Today I am going to explain the Faraday's law of electromagnetic induction. But before going to discuss the Faraday law, it is very important to understand what we mean by the magnetic flux. Magnetic flux is represented by this letter phi. And magnetic flux is measured as the number of magnetic lines, like you are having north pole of the magnet and south pole of the magnet. Then from north to south you are having the magnetic lines. Then there is some area between the magnetic lines, and those lines are crossing, like this line is crossing, this line is crossing, this line is crossing. Magnetic flux means how many lines are crossing the area. Okay, and it is written as flux is equals to BA cos theta, or flux is the dot product of B vector dot A vector. Like for this example, this is our area, right? And what is the direction of the area element? This arrow, it is the representation of the area vector direction. So flux is equals to dot product between B vector and A vector. Now in particular this case, the magnetic lines, they are along this direction because they are from north pole and towards the south pole. So magnetic lines are along this direction. And this is our area. What is the direction of the area? Direction of area is like this. And magnetic lines, they are also along the same direction. Both are along the same direction. Okay, when both are along the same direction, what is angle theta? It is 0, because theta is angle between B vector and A vector. Here theta equals to 0 and flux becomes cos 0 is 1, B into A simply. So this is magnetic flux, magnetic field multiplied by area, provided remember the theta angle also between B and A. Now in the same case, you think like if here is the north pole and here is the south pole, then magnetic lines direction from north to south, like this. But area vector, it is up, like this is our area vector along upward in direction. This is our B vector, north to south. What is the angle between the two? This angle is now 90 degree, and flux becomes BA cos 90. What is cos 90? Cos 90 is 0. The flux is 0. No line crossing this area. No line is crossing. Okay. So in previous case, all the lines were crossing through this area. But in second case, no line is crossing. Now then, if there is any other angle between area vector and, for example, this is our B vector, suppose, along this side, and this is area vector, then you have to consider the angle between the two, and flux becomes then B cos theta. This is very important to understand the Faraday law, Faraday and Henry law of electromagnetic induction. Okay, remember, flux means the magnetic lines which are crossing. Depends upon B, depends upon area, depends upon the theta angle between B vector and A vector. Keep in mind area vector direction. Any line normal and outward. Any line normal and outward. That is the area vector direction. This is all about the flux. Now I am coming Faraday law. Faraday and Henry law. Now this is our coil and there is a galvanometer is attached. Galvanometer can measure even a very small current flowing in the coil. The galvanometer is very sensitive. Okay. Now we take a magnet. You know, magnet north pole and south pole. Magnet having the magnetic lines like, okay, magnet having the magnetic lines. So this is a magnetic line. Now when the magnet is far away from the coil, a very few lines will be attached with the coil. Now you bring the magnet towards the coil. Okay, mean when north pole of the magnet is pushed towards the coil. When you pushed it towards the coil, like so when you pushed it towards the coil, more and more flux will link with the coil. The flux will increase. You know, flux is B A cos theta. You increasing the P mean it is pushed towards. So as the flux again it opposes, increases, you'll find a deflection in the galvanometer. Okay. Second thing you noted, if you pushed fast, if you move the magnet fast, okay, if it is fast, mean if the flux which, you know what happens when the magnet is pushed towards the coil, what happens? The flux which is linked with the coil, it changes. When it was far away, the flux was very small. When you are bringing it nearer and nearer, the flux increasing. That means flux link with the coil changes. When flux link with the coil changes, galvanometer shows a deflection. And if the change is rapid, if rapid change, fast change, you will notice a very large deflection. Large deflection means more current is flowing in the coil. That the result is when the flux linked with the coil changes, some galvanometer shows deflection, means some current is flowing through the coil. And that current is called induced current. Induced current. Okay. If it is moved slowly, like very slow, then there will be very small deflection in the galvanometer. Means the current induced will be small in the coil. If you moved fast, if there is a rapid change in flux, galvanometer shows more deflection. Though the result is changing magnetic flux induces the current. Now if the current is induced in the coil, because galvanometer is showing deflection, that means current is always induced if there is some induced voltage. That induced voltage is called EMF. This is induced EMF, induced voltage, induced by changing the flux, changing flux. And we noted it is proportional to, induced EMF proportional to rate of change of flux. Phi2 minus Phi1 over T. Phi1 was the initial flux when it is far away. You moved it. Then Phi2 is the flux when it is very close. Change in flux is Phi2 minus Phi1. Now time taken for this change. Time taken for this change is T. If T is less, it will be more. Mean you did it very fast. But if T is large, that you did it very slow. If T is large, means slow, change in flux, then EMF will be small. Now second thing, when you are bringing it, when you brought it closer and closer, what happened? The current flows in this loop in anti-clockwise direction. In anti-clockwise direction. Here the current will be in anti-clockwise direction. That means this face of the coil becomes north pole. And here the current, when you look the current along this side, this current will be clockwise. Clockwise means south pole. Mean when it is moved towards the coil, induced current is produced. Induced current magnetize this coil. Coil acquire magnetization, induced magnetization. This phase behaves like north pole. This phase behaves like south pole. Mean induced current flows in the coil in such a direction that the induced current opposes the motion of the magnet. Mean you are bringing it closer and closer. You are coming closer and closer, but the induced current opposes it, becoming the north pole here, becoming like to act north pole. As here, this phase behaves as a north pole, so it opposes the motion of the magnet. This is again important to remember. So this is proportional to d phi. I can say this is d phi upon dt. So EMF, induced EMF is minus some constant d phi by dt. Why minus sign? Because induced EMF opposes the motion of the magnet. And it is called Lenz's rule. Now coming this example, if the magnet is moved away, if it is moved away, again the induced current flows in the coil in such a direction that this phase then acts as a south pole and this phase acts as a north pole. Now what happens? In this case, when it is moved nearer and nearer, like if the current is flowing like this, in this direction, now when it is moved away, then current flows not like along this direction. Now current is supposed flowing along this direction. So that this phase, in previous case, this phase behaves as north. Now this phase now acts as a south pole because current is reversed if you moved away. Why so? Becoming south, it again opposes the motion of the magnet with attraction. Okay, it want to stop the motion becoming south by giving attraction. not to go away. Okay, it acts as south to oppose this motion. What happened now? Now the flux is again changing, but it is not increasing, it is decreasing. Again the induced EMF is produced, but the formula is the same. Maybe flux decreasing, maybe increasing. Induced EMF is produced. And induced EMF depends whether the change is fast or it is slow. Minus sign is again the opposition. It is giving again the opposition. Now instead of north pole, now if the south pole, if now the magnet is pushed towards the coil, the current flows in such a direction that it acts as a south pole. Induced current flows in such a direction. Now if it is moved away from the coil, induced current flows in such a direction that this loop acts as now the north pole, again giving opposition. So induced current which is produced, it always opposes it always opposes any change. So maybe magnet is moved away or maybe it is moved towards. Induced current always gives opposition, and that is called Lenz's rule. Second, I already explained that induced EMF or induced current which is produced, it depends what is the flux, it depends how much flux is changing and with what time it is changing. Negative sign means the opposition. If the magnet is kept stationary and you moved the coil towards or away, the same happened. Induced current is produced. That means it does not matter whether the magnet is moved or the coil is moved. Only it matters there should be relative motion between the two. One should move with respect to the second. Now, next thing which is very, very important, if the magnet is kept stationary here, okay, what do you see? Galvanometer shows then zero deflection. That means no induced current. There is flux when it is kept stationary. There will be the flux which is linked with the coil, but there will be no induced current. That means presence of the magnetic flux is not the reason of the induced current. The reason of the induced current is the change, the flux should change. May it increases, may it decreases. Then there is induced current. So flux should increase or decrease. Then the induced current flows. Not like that there is flux, only there is flux not changing, then there will not be any current. The flux change is important, not the presence of only flux is important. Okay. Number one, whenever the amount of the magnetic flux linked with the circuit changes and EMF is induced in the circuit, the induced EMF last means remains as there is change in flux is continue. As change in flux is continue. When you stops, then induced EMF vanishes. And again, the second, the magnitude of EMF induced mean amount of the induced EMF, mean amount of current, amount of the deflection in the circuit is directly proportional to the rate of change of magnetic flux. Negative sign because of the Lenz's rule, mean opposition. Induced current always gives opposition. Any type of motion, induced current always gives opposition to any change. And Lenz rule is important because induced current is we are having the induced current at the cost of the work done against the opposition. I mean, we are doing work against opposition, which is induced current is giving, and we are doing work, and that work then converted into the electric energy. So this is according to the conservation of energy. That the mechanical work done in moving the magnet towards or away, or you can say moving the magnet with respect to the coil, that work done changes into the electrical energy, producing the induced current. When we do not move the magnet, then work done is zero, and then there is no induced current in the circuit.